Is the night sky busy? It seems so, but most of its spectacular explosions occur in realms far beyond human comprehension. Hundreds of millions of light-years away, a silent explosion once ripped through a cluster of galaxies, sweeping through space with unimaginable force. Scientists suggest it was the largest energy release known since the Big Bang, yet there was no visible flash, only a void, larger than the entire Milky Way, expanding slowly and unstoppably through space. For eons, it went unnoticed, its scars hidden in the distant glow of X-rays, until human instruments finally captured the faint echo of that cataclysmic event. Why did it erupt? What triggered this incredible violence, and what does it reveal about how energy flows, accumulates, and bursts forth in the cosmos? Tonight, in our Exploring the Cosmos series, we delve into the origin of superclusters, what fuels their staggering violence, and the fundamental mechanics of energy on a cosmic scale. It's a vast story, but before we dive in, please don't forget to like and share. Superclusters are among the universe's most magnificent creations, a vast, intricate network woven from galaxies, spanning hundreds of millions of light-years. They are not singular objects, like a star or a galaxy, but massive collections of multiple galaxy clusters, loosely bound together by gravity. If the universe were a cosmic city, a galaxy would be a house, a cluster a whole neighborhood, and a supercluster an entire nation. It is within these colossal regions that most of the universe's matter and galaxies are connected, strung along invisible filaments of dark matter, yet simultaneously separated by immense cosmic voids, areas where almost nothing exists. Initially, when astronomers began mapping the distribution of galaxies on the largest scales, they expected to see a relatively random scattering of points, evenly spread through space. What they actually found was structure. Galaxies are not uniformly distributed but form intricate patterns, clumps, filaments, and walls. By the late 20th century, as technology advanced and telescopes began measuring the redshift for thousands of galaxies, a map of the cosmic web began to emerge. This network, made of long, thin filaments of galaxies and gas, is woven around gigantic voids, creating a honeycomb-like texture on the grandest scale. At the intersections of these filaments lie the superclusters, the most dense and complex regions of the universe's large-scale structure. A supercluster contains several galaxy clusters, each of which hosts hundreds or even thousands of galaxies. Scattered between these clusters are smaller galaxy groups, isolated galaxies, gas clouds, and the omnipresent, invisible presence of dark matter that helps hold everything together. Nevertheless, the gravitational bond between the individual clusters inside a supercluster is much weaker than the gravity within a single cluster. Over billions of years, the expansion of the universe slowly pulls these clusters apart. This means that while superclusters appear as unified entities now, they are more like temporary gatherings than permanent, gravitationally locked cosmic islands. To understand what a supercluster is, it helps to compare it with a galaxy cluster. Clusters like the Virgo or Coma cluster are dense, compact communities of galaxies tightly bound by gravity, where galaxies frequently interact. A supercluster is different. It's a much larger region that contains many such clusters, reaching sizes of 500 million light-years or even more. The largest known structure, the Hercules Corona Borealis Great Wall, spans about 10 billion light-years, a distance so vast that light takes nearly the age of the universe to cross it. Even so, this immense structure is not entirely gravitationally bound as a whole. More accurately, it is a massive, high-density region within the cosmic web. Astronomers identify superclusters by studying the distribution of galaxies across the sky and by measuring their redshift. By plotting millions of galaxies in three-dimensional space, we can see where matter tends to congregate. These clumps and filaments outline the supercluster structure. In modern surveys, the cosmic web reveals itself with astonishing clarity in the data. Galaxies form patterns of gigantic arcs and walls, interspersed with vast voids of empty space. One of the most famous examples is our home structure, the Laniakea supercluster, which contains the Milky Way. Laniakea spans about 500 million light-years and is home to approximately 100,000 galaxies. It is home to the Virgo cluster, which in turn hosts our local group, the small cluster that includes the Milky Way and the Andromeda galaxy. Defining where one supercluster ends and another begins is not straightforward. As the universe has no sharp boundaries, astronomers must rely on measurements of motion and density. Galaxies within a supercluster tend to move towards a common gravitational center, forming what are known as bulk flows. In the case of Laniakea, this flow directs galaxies inward towards the Great Attractor, a massive gravitational anomaly that is pulling many galaxies, including our own, towards it. It is this shared, cohesive motion that helps define Laniakea's boundaries and separates it from neighboring structures. Superclusters are not uniform in shape. Some resemble flattened walls, others are stretched into long filaments, and some look like knots. These differences stem from how matter collapsed under gravity after the Big Bang, where tiny density fluctuations in the early universe provided the seeds for later structure. Over billions of years, these regions accumulated more and more matter, forming galaxies and clusters, which then connected along the filaments of matter. Superclusters represent the largest scale of this process. They form the skeleton upon which the arrangement of galaxies is built. If we could strip away the stars and gas and only look at the dark matter, superclusters would appear as the bright nodes on the cosmic web, giving rise to everything we see. Without them, galaxies would be scattered like grains of sand, lacking a larger cosmic order. They also influence how galaxies move and interact. The gravitational pull from a massive supercluster can even bend the path of light from more distant galaxies through a phenomenon called gravitational lensing. This bending allows astronomers to map the distribution of dark matter, as visible matter alone cannot account for the strength of the observed gravitational effects. Even within a supercluster, there are smaller levels of structure, like the branching roads in a city, filaments that stretch for millions of light-years connect the galaxy clusters, guiding the flow of galaxies toward denser regions. Along these cosmic highways, galaxies merge, new stars ignite, and evolution continues. Superclusters also help scientists test theories about how the universe expanded after the Big Bang. Their size, shape, and distribution can tell us how matter was laid down in the early universe, and how dark energy is currently affecting the expansion of space. If the accelerating effect of dark energy continues, many of these immense structures will eventually drift away from each other, leaving isolated galactic islands surrounded by ever-growing cosmic voids. In the distant future, far-off superclusters will be pulled beyond the reach of our telescopes, their light stretched so thin by expansion that they will fade into darkness. For most of history, people imagined the universe as a relatively small, layered space, with the stars and the Milky Way marking the edge of existence. Later, we understood that the Milky Way is just one among billions of galaxies. Today, we know that even these galaxies are merely part of a structure so vast it challenges the limits of human imagination. Situated within the Laniakea supercluster, our Milky Way is but a tiny ripple in the cosmic ocean, drifting towards a massive gravitational center we can barely pinpoint. Yet, despite their immensity, superclusters are fragile on the cosmic timescale. They are held together only by a loose gravitational grip, and the universe's accelerating expansion will eventually pull them completely apart. The galaxies within them will continue their own motions, but the connections that define these vast regions will dissipate. The superclusters are thus both the largest and the most temporary of cosmic structures, a snapshot capturing a universe that is still expanding, still evolving, and still reshaping itself on an unimaginable scale. Looking at the largest scales, the cosmos resembles a net, a vast, delicate, filamentary network spanning space, forming the scaffolding that supports everything. Contained within these glowing threads is almost all of the universe's matter, both visible and invisible. However, as telescopes became more powerful and mapped the three-dimensional positions of galaxies, researchers noticed something striking. Long chains of galaxies forming arcs and walls, separated by immense voids spanning hundreds of millions of light years. These patterns could not be random, there had to be a grander, organizing mechanism shaping the arrangement of galaxies. The earliest clues appeared in the 1970s and 80s when large-scale redshift surveys first charted the universe's large-scale structure. The Harvard-Smithsonian Center for Astrophysics Redshift Survey provided the first striking images of the cosmic web. When the galaxies were plotted in a wedge-shaped slice of the universe, it eerily resembled a sponge or a spider web, with long filaments connecting dense nodes of galaxy clusters. This discovery stunned astronomers. For the first time, the universe didn't look like a random sea of stars, but a structured, interconnected whole. These filaments are the true skeleton of the universe. They are composed primarily of dark matter, the mysterious, invisible substance that makes up about 85% of all matter in the cosmos. It gravitationally pulls on visible matter, bends light, and influences the motion of galaxies. Within these dark filaments, gas and dust clouds congregate, providing the raw material for galaxy formation. The galaxies we observe are like lights strung along these invisible threads. Between the filaments are the colossal voids, vast regions almost entirely devoid of galaxies. The contrast between the dense filaments and the sprawling voids gives the universe its distinctive honeycomb appearance in three-dimensional mapping. The largest voids can stretch for hundreds of millions of light years, acting as massive cosmic deserts separating busy centers of galactic activity. The sheer size of these voids raised questions about how the universe could have become so non-uniform. The answer, as cosmologists discovered, lies in the physics of the early universe. Shortly after the Big Bang, the universe was almost uniform, filled with hot plasma, with only infinitesimally small differences in density. These minute fluctuations served as the seeds for all future structure. As the universe expanded and cooled, Gravity began pulling matter towards the slightly denser regions, and over eons, the differences were amplified. Billions of years later, this process sculpted the universe into the structure we see today. Numerical simulations demonstrate this process in stunning detail, how those initial seeds slowly clumped together to build the net-like framework we observe today. The cosmic web is more than just a pattern of galaxy distribution, it is an ecosystem. Filaments funnel gas to galaxy clusters, resupplying them with material for new stars. Where two filaments intersect, the combined gravity forms massive nodes, the location of superclusters. These intersections are the cosmic crossroads where galaxies collide, merge, and evolve more rapidly than those in quieter regions. Everything that happens on small scales, star formation, galaxy evolution, black hole growth, is ultimately governed by the galaxy's position within the larger cosmic web. Scientists have found ingenious ways to study this hidden structure. Since dark matter neither emits nor absorbs light, researchers observe its influence through the gravitational lensing effect. This has revealed the filaments connecting clusters and superclusters, validating simulation predictions. In 2019, astronomers even directly imaged a section of one such filament, a 50 million light-year bridge of gas connecting two galaxy clusters. This was the first direct image of the gaseous component of the cosmic web, turning theory into tangible evidence. Leviathans like the Ophiuchus supercluster are distributed along these filaments towards massive knots in the cosmic web. Within them, galaxies are not only affected by the gravity of their own cluster but also by the pull of neighboring superclusters along these invisible threads. The flow of galaxies, gas, and dark matter along these connections forms a dynamic network spanning hundreds of millions of light-years. Observing these vast connections is difficult because most of the web is incredibly faint and diffuse. A significant fraction of its mass exists in the form of warm hot intergalactic medium (WIMP) gas. This gas is heated to millions of degrees, yet it is too faint to be seen directly with optical telescopes. X-ray and radio observatories reveal this hidden mass by tracking the radiation from this invisible matter and its interaction with cosmic rays. When mapped, they show the long, filamentary bridges between clusters, the arteries of the cosmic web, which supply galaxies with matter and shape their evolution over time. Every supercluster sits within this interconnected framework. There are no truly isolated corners of the universe, even regions separated by hundreds of millions of light-years are subtly connected through the weak pull of gravity and the faint glow of gas. When simulating the entire observable universe, superclusters are seen connected by these luminous threads, forming a network that extends in every direction. From our perspective, it is like being inside a vast cosmic organism, where the filaments are the veins and the galaxy clusters are vital organs. This idea of interconnection on such an enormous scale has transformed scientists' understanding of cosmic evolution. Galaxies are not independent actors, their position in the web determines their destiny. Galaxies near dense filaments are more likely to form stars and interact frequently, while those adrift in the quiet voids evolve slowly and in isolation. The web is both a bridge and a boundary, channeling matter where it is needed while keeping other areas sparsely populated for eons. As the universe continues to be mapped, the cosmic web is becoming clearer, yet also more mysterious. Every new survey reveals more filaments, more hidden structures, and more colossal connections between areas once thought to be unrelated. Even our own Laniakea is just one part of a larger flow field that sweeps up Ophiuchus, Perseus Pisces, and countless other superclusters, perhaps forming the ultimate pattern of the universe, a continuous structure that connects nearly everything. The Ophiuchus supercluster is located approximately 390 million light-years from Earth, nestled deep within the constellation Ophiuchus, a frequently overlooked region that holds some of the universe's most powerful and mysterious structures. To the naked eye, Ophiuchus is just a faint smattering of stars, but behind it lies a massive, gravitationally bound gathering of galaxies Shutterstock, constituting one of the most immense superclusters in our cosmic neighborhood. Its mass, scale, and complexity make it a galactic metropolis in the cosmic web, a massive hub where multiple filaments intersect. From our vantage point, the Ophiuchus supercluster is not cosmologically distant. It neighbors other grand structures, such as the Shapley concentration and our own Laniakea supercluster. It spans an area of sky hundreds of millions of light-years across, containing several large galaxy clusters. Galaxies within it are strung along invisible dark matter filaments, clustering and chaining together to form the intricate assembly of the Ophiuchus supercluster. Mapping this region was initially challenging. Ophiuchus is near the plane of the Milky Way, where dust and gas obscure large portions of the more distant universe, an area astronomers call the zone of avoidance. The bright stars and thick clouds of our galaxy long kept vast swaths of the cosmos veiled. However, using X-ray and radio telescopes, scientists were able to penetrate this curtain, revealing one of the local universe's greatest concentrations of matter. Their discovery was extraordinary, a structure comparable in density and energy to the renowned Shapley supercluster. The heart of the Ophiuchus supercluster is the Ophiuchus galaxy cluster, which is one of the brightest and largest X-ray sources in the sky. Gas compressed and heated to tens of millions of degrees makes the cluster shine fiercely, visible even across hundreds of millions of light-years. At the cluster's center is a massive elliptical galaxy, and lurking in its core is a supermassive black hole, an engine capable of reshaping its environment on colossal scales. The outer layers of the cluster are surrounded by numerous smaller galaxy groups and streams of galaxies, all under the sway of the supercluster's gravitational field. These structures are not static. They are slowly drifting, merging, and rearranging under the pull of dark matter. To grasp its scale, consider this: traveling across it, even at the speed of light, nearly 300,000 kilometers per second, would take hundreds of millions of years. This region is scattered with thousands of galaxies, each containing billions of stars, planets, and countless possible worlds. The combined mass of all these galaxies, their surrounding dark matter halos, and the galaxy cluster gas makes this supercluster one of the dominating structures in the local cosmic landscape. Like all superclusters, Ophiuchus is not permanently bound. Billions of years from now, as the fabric of the universe stretches, its galaxy clusters will become increasingly isolated. But for now, these structures remain a connected whole, making it a huge hub of activity in our nearby cosmic domain. Mapping the Ophiuchus supercluster has been challenging. The dust of the Milky Way blocks the visible light from many of its galaxies, forcing astronomers to rely on X-ray, radio, and infrared observations. By stitching this data together, researchers have sketched a clearer image, revealing a gigantic structure spanning over 300 million light-years. The galaxies within the supercluster are spread along filaments that connect it to other significant superclusters. These filaments are the cosmic highways that continuously funnel fresh gas and new galaxies into the Ophiuchus region, keeping it active and continuously evolving. Astronomers studying Ophiuchus describe it as a bridge, connecting dense, crowded regions of the local universe to sparser, more distant ones. Because it is relatively close to the Milky Way, it offers a rare, detailed look at the behavior of such a colossal system. Observations show that the central regions of the supercluster are dominated by massive elliptical galaxies, ancient systems that formed early in the universe, while the outskirts feature younger spiral galaxies, rich in gas and actively forming stars. This diversity reflects the different evolutionary paths galaxies take depending on their location. Those near the dense core experience frequent interactions and mergers, while those along the outer filaments proceed more slowly and in isolation. Simulations suggest that the dark matter filaments extend far beyond the visible galaxies, linking Ophiuchus to neighboring superclusters and clusters. These invisible bridges act as conduits for the flow of matter, delivering sustenance to the supercluster's core. The galaxies we see today are simply the bright markers on a grander, unseen framework. The Ophiuchus supercluster also helps us understand the transition between local and larger cosmic structures. It sits near the boundary of other superclusters, such as Laniakea and Perseus Pisces. Some research suggests that the flow of galaxies in this region may be influenced by both, hinting at a larger pattern of movement spanning hundreds of millions of light-years. In this sense, Ophiuchus is both a structure unto itself and a connecting node in the cosmic web that binds the universe together. Galaxies within Ophiuchus are not passive passengers. Many bear the scars of past collisions, distorted shapes, long tidal tails, and bursts of star formation triggered by gravitational encounters. The galaxy clusters within the supercluster are still merging, releasing shock waves into the intergalactic medium that heat the surrounding gas and trigger localized star formation, driving the cycle of cosmic evolution forward. Even the faint X-ray and radio background glow there tells an epic story of violent motion and change, a continuous drama enacted by galaxies under the forces that dominate the universe. Because of its high mass and activity, the Ophiuchus supercluster serves as a crucial laboratory for studying the large-scale interaction of matter, dark matter, and energy. Observing the behavior of galaxies and gas within it gives scientists insight into how gravity carves out the universe and how dark energy drives expansion. The intense X-ray emission from the Ophiuchus cluster provides valuable data on the temperature and density of the intergalactic gas, revealing how matter behaves under extreme conditions. Meanwhile, radio observations uncover the remnants of ancient black hole eruptions and the colossal magnetic fields that permeate the supercluster space. From our small corner of the Milky Way, the Ophiuchus supercluster may seem impossibly distant, but on a cosmic scale, it is right next door, a realm of galaxies that silently influences us. It is a reminder that even the local universe is just part of a larger whole, a network woven from colossal structures, each witnessing the shaping of the cosmos under the long-haul work of gravity. Everything began with a subtle irregularity. When NASA's Chandra X-ray Observatory and the European XMM Newton telescope turned their eyes towards the Ophiuchus galaxy cluster, astronomers noticed subtle distortions in the diffuse glow. The X-ray brightness wasn't uniform, it seemed to fluctuate, as if the hot plasma filling the cluster had been stirred or disturbed by some force. The edges of the glow showed strange curvature, as if a giant wave had passed through the medium. These were not the signs of a tranquil system in equilibrium, but scars etched across millions of light-years of space. Initially, scientists were cautious. Galaxy clusters are dynamic places, mergers, collisions, and black hole activity constantly reshape the environment. Sloshing and currents of gas are not uncommon. But the magnitude of the disturbance observed in Ophiuchus was far beyond anything seen before. The X-ray data revealed a massive, faint cavity where the hot gas appeared to have been pushed aside. This wasn't a small pocket of vacuum, but a colossal bubble spanning hundreds of thousands of light-years. As astronomers scrutinized the data, the cavity's shape became clearer. It was offset from the cluster center, looking like a void scooped out of the surrounding plasma. This could not be caused by gravitational motion alone. Some force emanating from the cluster's center must have pushed the gas outward on a scale far exceeding that of the Milky Way. To understand this force, researchers looked to the galaxy at the cluster's center. In most clusters, the central galaxy acts as a gravitational anchor, its core often harboring a black hole that periodically wakes up, devouring gas and dust and releasing energy in powerful jets. While explosive, most of these eruptions are relatively mild on a cosmic scale. They heat the surrounding gas, regulating star formation and maintaining a delicate balance in the cluster core. But in Ophiuchus, something had occurred that went far beyond this routine cycle. Combining X-ray and radio observations, scientists pieced together the evidence. The cavity in the X-ray glow aligned perfectly with faint radio emission, the signature of charged particles accelerated by a past explosion. This radiation showed that the cavity was filled with radioplasma, the remnant of an ancient eruption that had blown out from the center and swept through the cluster hundreds of millions of years ago. What they were looking at was not just a typical black hole feedback event, but the fossil of the most powerful known explosion since the Big Bang. When the sheer scale of the event was calculated, the results were astounding. The eruption released hundreds of thousands of times more energy than any supernova, and was several times more powerful than the previous record holder, an eruption in the galaxy cluster MSO 735.6 plus 7421. The total energy was so immense it could power all the stars in the entire Milky Way for billions of years. It was as if a cosmic volcano erupted in the heart of the Ophiuchus cluster, ejecting matter with enough force to reshape space. The cavity left behind by the explosion is estimated to be 1.5 million light-years wide, enough space to fit 15 Milky Way galaxies side by side. Even more astonishingly, this discovery was almost missed. It was only with the combined focus of X-ray and radio telescopes that astronomers could see the true picture. In optical telescopes, Ophiuchus still appears calm, its galaxies merely twinkling in the dark. In other wavelengths, it presents unimaginable violence, a region permanently scarred by a primordial cosmic blast. The culprit for this eruption is almost certainly the supermassive black hole at the cluster center. In the distant past, it entered an active phase, gorging on huge amounts of gas and spitting out relativistic particle jets along its axis of rotation. These jets quickly expanded, pushing the hot gas aside and forming the immense cavity we see today. After the jets subsided, they left behind a region filled with low-density, magnetized plasma, which is the faint radio glow astronomers detected millions of years later. What makes this more amazing is that such energy didn't destroy the cluster. Despite the unimaginable energy released, the Ophiuchus cluster remains largely intact. The blast was violent enough to punch a hole in its gaseous atmosphere but not enough to tear the entire system apart. This suggests a delicate balance of creation and destruction. The same black hole that wreaked havoc also prevents the core gas from cooling uncontrollably, regulating the flow of matter over cosmic timescales. It is a cosmic paradox. The most violent force also brings about long-term stability. For years, the clues to this eruption were hidden in the data, dismissed as minor irregularities or overlooked as instrument artifacts. It wasn't until researchers combined data from multiple observatories, Chandra for the X-rays, XMM Newton for confirmation, and radio arrays in Australia and India to capture the full radio map, that the complete picture emerged. When they overlaid the maps from different wavelengths, the alignment of the X-ray cavity and the radio lobes was undeniable. This was no ordinary feature. Its size, shape, and energy pointed to an unprecedented explosion. In that moment, a seemingly stable galaxy cluster was transformed into a grand archive of cosmic violence. This discovery changed the understanding of galaxy clusters and black hole activity. Previously, there was an assumed upper limit to the energy even the most massive black holes could release. The Ophiuchus eruption shattered that assumption, demonstrating that under certain conditions, black holes can unleash energy potent enough to reshape millions of light-years of space. These events may be rare, perhaps occurring only a few times every billion years across the entire universe, but their after-effects are profound. They redistribute gas, alter the growth of galaxies, and influence how matter cools and collapses in the core. Even today, the ripples of this blast still resonate through the Ophiuchus supercluster. The displaced gas is slowly falling back towards the center, stirring up currents and shock waves that propagate through the cluster's gaseous atmosphere. These disturbances, similar to sound waves traveling through the air, may persist for hundreds of millions of years, eventually dissipating as they travel. In a sense, the Ophiuchus cluster is still echoing its past, an echo that reaches us as a faint X-ray and radio hum across the void. When astronomers discuss the Ophiuchus explosion, it is easy to imagine an instantaneous cosmic conflagration, releasing incredible energy in a moment. But this image is misleading. Explosions in the cosmos are not like those on Earth. There is no sharp flash, no deafening sound rushing through the air, only the slow stirring, shaping, and pushing of space itself by unseen energy over eons. Cosmologically speaking, what we call an explosion is more like a long exhalation. The energy release is so massive that even the fastest processes take millions of years to play out. The Ophiuchus cluster eruption spanned a timescale almost beyond human comprehension. Scientists estimate it lasted for hundreds of millions of years, perhaps close to a billion. Over this duration, the central black hole steadily injected energy into the surrounding gas, slowly inflating the gigantic bubble as if in slow motion. Imagine a balloon being inflated, not in seconds, but over the entire evolutionary history of mammals. That is roughly the pace of the Ophiuchus cavity. The shock front advanced perhaps only a few light years per year. For a cluster nearly 1.5 million light years across, this is almost imperceptible. On the timescale of human civilization, the event is virtually frozen. If we had been watching Ophiuchus from the beginning, we would not have seen any dramatic change in a human lifetime. The cluster would appear quiet and unchanging. Yet, beneath this surface tranquility, the black hole jets were continuously sculpting the cosmos, moving trillions of tons of hot gas and slowly carving out a cavity the size of multiple galaxies. To truly grasp such timescales, we must stretch our imagination. The entire recorded history of human civilization, every empire, every invention, every generation, spans only a few thousand years. The Ophiuchus eruption may have lasted tens of thousands of times longer. From the appearance of multicellular life on Earth to the rise of humanity, this cosmic engine may have been silently operating. The start of this event, like most black hole eruptions, began with accretion. In its normal state, the supermassive black hole consumes gas and dust at a modest rate, emitting only faint radiation as matter falls toward the event horizon. But in Ophiuchus, something tipped the scales. The black hole suddenly gained a massive fuel supply and converted the mass of that matter into energy with astonishing efficiency. Not all the gas was swallowed. Some material, guided by the black hole's magnetic fields, was channeled along its axis of rotation to form twin jets, which were ejected at speeds close to that of light. Crucially, this energy wasn't released all at once, but injected continuously, more like a blowtorch than a bomb. Over tens or hundreds of millions of years, the jets expanded into giant lobes, filled with high-energy particles and magnetic fields, slowly hollowing out the huge cavity now visible in X-ray images. At any given moment, the process was gentle by human standards, but the cumulative effect of countless moments resulted in the largest explosion ever witnessed by humanity. Up close, the process would have been silent. There is no sound in space, and the cluster's thin gas cannot transmit vibrations. The only noise was the radiation, radio, X-rays, and gamma rays, flickering faintly against the cosmic background. The jets were visible in radio light as long, glowing streams, slowly changing shape as they interacted with the surrounding gas. It was an event that was both incredibly violent and eerily quiet, like watching a slow tide of energy move through a thick medium. The slow pace of cosmic change often deceives us into thinking the universe is static. Ophiuchus proves that even the largest structures are constantly in motion, but on timescales far exceeding our senses. The image we have of the cluster today is a single still frame in a story that has been going on for hundreds of millions of years. Every photon of light arriving today left its source long before modern humans evolved. If the history of the Ophiuchus eruption were compressed into 1 year, a day would represent several million years. The black hole would ignite on January 1st, beginning to puff out plasma. By June, the cavity would just be starting to form, small and faint. By August, the surrounding gas, compressed and heated, would begin to glow. It is only late in the year, approaching December, that the cavity would grow to its current colossal size and the energy would begin to decay. And this cosmic year corresponds to almost 1 billion years in reality. This enormous timescale also dictates how we study it. Because the evolution is so slow, tracing changes directly is nearly impossible. Scientists must piece together a timeline by capturing snapshots of different systems at different stages. One cluster might be just igniting its jet, another has a fully formed cavity, and a third has only the fading remnants of the event. Together, they form a cosmic time lapse built from static pictures. The after effects of the Ophiuchus eruption are still present. The cavity, filled with magnetic fields and relativistic particles, is slowly cooling and diffusing. The surrounding gas is still hotter than models would predict, a testament to the ancient heat injected there. These scars will remain for hundreds of millions of years, their subtle shifts in temperature, density, and motion providing later astronomers with the ability to read the echo of the blast. In space, time seems to slow down, a shock wave can travel for millions of years, and the energy released in a single event can take billions of years to fully dissipate. The Ophiuchus cavity is thus a memory frozen in the fabric of the cosmos. On a universal timescale, our fleeting millennia are negligible, but the symphony of the Ophiuchus explosion is still resonating through the cluster's hot gas. What we hear with our telescopes today is not a recording of a past time, but the finale of a process still unfolding, its long tail stretching across cosmic time. At the very heart of the Ophiuchus cluster is the supermassive black hole. We tend to think of black holes as always consuming, always destroying, but for most of their lives, they are almost entirely silent, sitting at the center of their galaxies, surrounded by vast clouds of gas and stars. Despite having the gravity equivalent of hundreds of billions of suns, they barely shine, making them incredibly difficult to detect. Yet, when conditions are right, these sleeping giants awaken, and when they do, they are powerful enough to reshape vast swaths of space. The black hole within Ophiuchus is estimated to have a mass of several 100 million times that of our Sun. To put that in perspective, if placed at the center of our solar system, its event horizon would be larger than the orbit of Mercury. Its gravity is so intense that not even light can escape. Yet, paradoxically, some of the brightest objects in the universe are powered by such black holes. Their light does not come from the black hole itself, but from the material spiraling into it. In the maelstrom of the accretion disk, energy and chaos are unleashed. Astronomers believe the Ophiuchus black hole had a prolonged period of activity. Perhaps a neighboring galaxy swung too close, and its gas was gravitationally stripped away, or perhaps the long-term accumulation of matter in the cluster core finally pushed the system past a critical point, and gas rushed inward. The matter falling into the black hole does not instantly vanish. Instead, it is first heated by friction and magnetic forces into a colossal, blazing accretion disk. According to Einstein's famous formula, a tiny fraction of this mass can be converted into energy far exceeding that of a nuclear bomb. However, not all of this energy escapes as light. A significant portion is channeled and ejected through narrow jets along the black hole's poles. These are among the most powerful structures in the universe, with charged particles streaming along coiled magnetic field lines at speeds close to that of light. In smaller galaxies, these jets may extend for thousands of light years. In galaxy clusters, they can stretch for millions. It is these very jets that astronomers believe carved out the massive cavity confirmed in 2020. What is most compelling about events like this is how they blur the line between destruction and shaping. The black hole is not just consuming, it is also sculpting. By injecting energy into the cluster gas, it prevents the gas from cooling too quickly and collapsing into new stars, altering the balance of gravity and pressure, and slowing down the evolution of the galaxies within the cluster. This feedback mechanism is now considered a key part of galaxy and cluster evolution. When a black hole becomes too active, it can eject enough energy to push away the very gas that feeds it, thereby starving itself. When the gas eventually cools and falls back, the process restarts, a cycle of dormancy, eruption, stillness, and explosion. The Ophiuchus black hole likely experienced this same rhythm, dormant for eons, then suddenly awakening to unleash a storm that inflated the entire cluster, until the jets faded and the accretion disk thinned, leaving it quiet again, with only the massive scar we see today. To explain how the jets are launched, we must go to one of nature's most extreme locations, the thin layer just outside the event horizon. There, spacetime is severely warped by the black hole's spin, and the magnetic fields threading through the accreting plasma become tightly wound and stretched, like a coiled spring being torqued. Once released, this sends energy screaming outward along the magnetic field lines. This process is known as the Blandford-Nyack mechanism, which can convert the black hole's rotational energy directly into kinetic energy. In other words, the black hole uses its own spin to power the eruption. The faster it spins, the more energy it can release. The Ophiuchus A black hole likely spun rapidly during its active phase, potentially near the speed of light at the equator, providing the immense energy reservoir required to sustain the jet for hundreds of millions of years. Over time, the jets become unstable, interacting with the surrounding gas, bending and twisting, and eventually ballooning out into the lobes and cavity we see today. The irony is that despite its power, which affects a region millions of light-years across, the black hole itself is still tiny compared to the cluster. Its event horizon could fit within a single star system's orbit. The cosmic paradox is once again evident. The smallest, densest object sculpts the largest, most diffuse structures. The aftermath of the eruption dramatically changes the landscape around Ophiuchus A. Galaxies near the black hole may have been flooded with radiation, the intergalactic gas blown away or heated to extreme temperatures, making new star formation difficult, and existing stars potentially stripped of their outer layers. The entire central region would have glowed intensely in X-rays, the signature of that extreme heat. As the energy slowly dissipated, the cluster returned to a slow calm, the cavity cooling and filling with radioplasma. Even in silence, the black hole's influence persists. The surrounding gas carries its fingerprints, subtle motions, temperature gradients, and magnetic ripples tracing the path of the ancient jet. Astronomers read these relics like geologists read layers of volcanic rock, piecing together the black hole's history, a record of quiescence and bursts of activity, of how a cosmic engine reshaped its environment over billions of years. How does one measure an explosion so vast, so distant, and so old? The event we are trying to understand occurred hundreds of millions of light-years away and spanned timescales far exceeding human reference. There was no direct visible light signal, no shining fireball or expanding debris cloud like a supernova, only the faintest scars remained. Scientists had to reconstruct one of the most powerful cosmic events in history from these subtle clues. The work began with a telescope that cannot see visible light, the Chandra X-ray Observatory, in orbit since 1999. It is specialized in studying X-rays, the light produced by the hottest, most energetic regions in the universe. Galaxy clusters like Ophiuchus glow brightly in X-rays because the intergalactic gas is heated to tens of millions of degrees. Within this luminous cloud, astronomers can read the hidden dynamics, where the gas is denser, where it is sparser, where it has been pushed aside, and where violence has occurred. When Chandra observed Ophiuchus, the image wasn't the smooth, elliptical glow typical of most clusters. Instead, it showed a strange curved boundary on one side, a faint edge where the X-ray brightness suddenly dropped off. This hinted that something had blown a giant bubble in the cluster's gaseous atmosphere, but the Chandra data alone wasn't enough to determine its full scope. Researchers cross-referenced it with earlier data from the XMM Newton telescope. This telescope, also dedicated to high-energy light, has a wider field of view and was able to trace the fainter outline of the cavity. The results showed that it was not just large, but colossal. The cavity spanned approximately 1.5 million light years, as if an invisible giant had scooped out a huge chunk of the Ophiuchus cluster's gaseous ocean. The next question was obvious: how much energy was required to move that much matter? The answer came from the physics of the cluster. The hot gas in the cluster can be approximated as a fluid, and when something pushes it aside, the resulting cavity has a measurable physical signature. By knowing the pressure of the gas surrounding the cavity and the volume of the cavity, scientists could estimate the amount of work done, which equates to the energy released by the eruption. The concept is simple, the numbers are astronomical. The calculation was stunning, roughly equivalent to hundreds of millions of gamma-ray bursts combined. It was several times more powerful than the previous record-holding eruption in the MSO 735 cluster. Energy cannot be created from nothing. The clues led back to the central galaxy and its supermassive black hole. The direction of the cavity aligned with the direction of faint radio jets seen by earlier radio telescopes. Radio astronomy does not detect light, but rather the long wavelength electromagnetic signals produced by electrons spiraling in magnetic fields. Overlaying the radio and X-ray maps completed the picture, like excavating a fossilized explosion. The event was over, but its imprint was perfectly preserved in the cluster's energy fields. By comparing the brightness and shape of the radio lobes to jet models, astronomers could even estimate the duration of the eruption. These findings were hard-won. Eking out a signal from hundreds of millions of light-years away is like trying to hear a whisper across an ocean. Chandra's X-ray data is composed of individual photons, accumulated over hundreds of hours of exposure. Every photon is precious, carrying information about the energy and location of its origin. Researchers spent years processing the images, removing noise, and combining multiple observations to sharpen the view. The radio data likewise required rigorous calibration. Ground-based arrays are affected by atmospheric and terrestrial interference, as well as the cosmic background. Isolating the faint trace of an ancient radio lobe from all this noise required patience and technology that didn't even exist when the event began. Initially, the arc in the X-ray image was sometimes dismissed as an artifact, perhaps a calibration issue or an eccentricity in the image. It took years of multi-wavelength follow-up to provide the irrefutable evidence that settled the matter. The technique for measuring the energy of these eruptions relies on layering these different data sets. X-rays provide the density and temperature of the gas, radio shows the location of the relativistic particles, and sometimes optical and infrared images can identify the host galaxy or black hole. By combining these, astronomers can build a three-dimensional model of how the jets inflated, how the gas responded, and how the structure evolved over time. Through this method, the Ophiuchus eruption became the benchmark case for understanding extreme black hole feedback. Where previously scientists believed there was an upper limit to the power of a black hole eruption, Ophiuchus broke it. Under the right conditions, a supermassive black hole can release energy comparable to the total output of an entire galaxy cluster, an object only a few 100,000 kilometers across, reshaping millions of light-years of space. Every calculation of energy and distance is an attempt to build a bridge from the human scale to the cosmic. Even so, the measurement comes with uncertainties, the numbers carrying error bars. The model relies on assumptions about the gas density, temperature, and geometry. Some speculate the true energy might be higher, others suggest it could be slightly lower. But no one doubts its magnitude. It was an incredible cosmic blast that pushed the boundaries of what is possible for black holes and the universe itself. Every X-ray photon, every radio wave, is a letter in that ancient narrative, pieced together to tell a story not just about the power of a single black hole, but about the hidden dynamics that run the cosmos, a universe that etched its greatest explosion permanently into the faint glow of a distant galaxy cluster. This concludes our knowledge share for today. May you have a restful dream and a good day. We will see you next time.